Have you ever wandered through a scrapyard and came across the parts of a monster just lying there in the wreckage? Well, that's how this machine came into being. This resonant tower is known as a Tesla coil. This particular one is just over 17 feet tall, and it can generate about 1,000,000 volts at 60,000 cycles per second. Today we'll cover the chaotic history of this machine, then explore a scheme to boost its strike energy far beyond the traditional Tesla coil architecture. This coil began its life in 1990 at a local scrapyard I'd often visit in West Oakland. They had just started to demolish a huge, ancient generator house, and their lot was quickly filling up with tons of quality buswork and switchgear. Now, any reasonable person who witnessed these piles of scrap would have thought, hey, here lies all the parts for a Tesla coil of proper dimensions. But one question remained. Where on earth could you drag several tons of scrap and assemble such a beast? Survival Research Laboratories was by far the best option. SRL was the ultimate machine shop, filled with machine tools of every imaginable form. Survival Research Labs was also unique in that it didn't have the normal commercial motivations. Their main focus was to explore the extreme corners of machine design space. Inevitably, this resulted in the creation of many temperamental machines, which would often get into conflicts and direct large amounts of fuel and ordnance at each other and their local surroundings. So, after unloading a few truckloads of scrap, we began construction of the coil tower at SRL. After a few months of heavy fabrication and precision machining, and winding nearly a mile of secondary wire onto the coil form, the main parts of the coil tower came to life. You might say that the new Tesla tower experienced a baptism by fire of sorts, since it was immediately thrust into several hostile SRL scenarios. But the new coil tower held its own against the hostile machines it encountered there. The coil even committed suicide once, in the true survival research machine tradition. Strangely enough, this scrapyard coil turned out to be the largest operating coil in the world at the time, which presented us with several challenges towards operating this beast at full power on a very limited budget. For instance, all Tesla coils up to this point used single-phase AC power, but 40,000 watts was beyond the capacity of most single-phase AC feeds. So this became the first Tesla coil to use three-phase AC power. Ironically, not even Tesla's own coils used his patented three-phase power system. This was because Tesla didn't have an easy way to combine the three power phases into a single coil. Today, however, we can combine the three phases quite easily using an array of heavy high-voltage diodes. What do you suppose Tesla might have given for a set of these diodes from the future? On the other hand, Tesla might not have been very enthusiastic about using DC to solve the problem. But with high-voltage DC, the operator can now directly control the output power through the simple expediency of changing the rotary gap speed. This is far cheaper and easier than using the large adjustable transformers needed for traditional AC-driven coils. This was also the first Tesla coil to use discrete ring elements to form the toroidal high-voltage electrode. This was because a solid metal toroid of this size would have cost a king's ransom. So, instead, we rolled aluminum pipe from the scrapyard into rings and TIG welded them into a discrete element form. The discrete element toroid seems to support long high-voltage arcs quite well. Tesla coils can produce fantastically high voltages through the magic of resonant rise. However, this also results in equally low output currents. Although Tesla coil arcs can reach across large distances, their low currents do little damage to grounded objects. They're even routinely used as stage props in harmless performances. One way to make the Tesla tower far more effective against hostile machines would be to boost its output current to the levels found in natural lightning. To do this, We need to wait for the exact instant that the streamer makes contact with the target. Then immediately after that instant, find some way to dramatically increase the Tesla primary energy. This critical instant is of key interest, since the plasma channel transforms from what is known as a voltage-driven regime into a current-driven regime. Right at this transition, there's a brief time where the arc could transport a high current pulse with virtually no limit, if we just had a precise way to inject a high current pulse. One way to launch the high energy pulse at this critical moment is a clever scheme called a pulse forming network. It's a critically tuned ladder of high energy capacitors and inductors, carefully designed to form a high energy pulse and pass it safely through to the target, rather than into the components of the Tesla tower itself. This last part is especially important if we wish to perform the experiment more than once. Now, to test this theory, all we need is a suitable pulse-forming network. Well, we happen to have one right here. This pulse-forming network can deliver a shaped pulse of over 50,000 amps, with a total energy of about 1,057 times the tower primary energy. If the pulse-forming network can actually boost the output energy by over 1,000 times, we'll need a more precise way to direct the arcs towards the intended target. Otherwise, the coil tower would throw high-energy strikes in random directions at the surrounding objects and people. That would be irresponsible and a poor demonstration of machine control. Towards improving machine control, I've designed and installed this field focusing electrode, which will allow the operator to launch the arc discharge towards the actual target. The field focusing electrode features an aiming servo and laser, which allows the operator to align the electric field focus with the target. I'll be operating the coil tower and the booster from the relative safety of the operator's console here, with suitable eye and ear protection, of course. Please, don't try this at home. Let's start out with just the normal, unboosted 1 million volt discharge to establish a baseline. We'll use this 4-foot fluorescent tube to indicate any increase in the strike current. As we can see, the tube illuminates just a bit when the normal arc discharge strikes it. If we add a diffraction grating, we see that the arc has a very different spectral content than that of the tube. The sharp red and green lines are the colors you'd see in an aurora borealis. Now let's charge the pulse-forming network about halfway and see if the tube brightness noticeably increases. If the pulse-forming network can fire right on the critical transition, then the tube should become noticeably brighter. It looks like the pulse-forming network found the transition slot. Unfortunately, it also exceeded the energy rating of the diagnostics by a critical margin. At this frame rate, the tube can show each individual high-voltage pulse until its state of fragmentation becomes too great. Even after areas of the plasma channel become dark, the high-voltage pulses show that they remain highly ionized. To measure the effects of the boosted arc on 3D structures, I've arranged a couple of test fixtures here. Again, let's start with just the unboosted 1 million volt output to see how the arc will attach to the structures. Notice how the taller water tower takes all of the strikes on its lightning rod and shields the church steeple. This shielding effect works in a similar fashion on full-scale structures against lightning strikes. Also note here how the normal Tesla tower currents are far too weak to affect the water tower. Now let's measure the effect of boosting the strike currents. For this test, we'll double the previous boost energy, which is still within the operating limits for the pulse-forming network. 3, 2, 1. As we can see, doubling the boosted energy provided adequate margin for this evaluation. When the lightning rod vaporized, the superhot plasma trapped inside the water tank produced enough pressure to escape in a rather nonlinear fashion. It also turns out that highly molten 3D printed plastic is quite flammable. The high voltage arcs also demonstrate that the flames remain quite conductive. Fortunately, full-scale water towers are made from a less flammable material. One might wonder what would happen now, given that the shielding effect of the water tower is gone. Let's use the empirical method to find out. Note the St. Elmo's fire forming on the church steeple, similar to the fires seen on the masts of ships in lightning storms. This is usually an omen for an unexpected descent of energy in the near future. The increased electric field on the unshielded steeple led to a direct arc strike, and ultimately to a loss of structural integrity. So how effective would the boosted coil tower be against hostile machines? One critical component on these hostile machines is the fuel tank. It turns out that fuel tanks made out of steel easily shield the fuel against normal unboosted arc discharges. But could a high current strike actually penetrate the tank wall? Let's find out. Since we're dealing with steel here, let's go with the full level of charge. 3, 2, 1. It appears that a full boost was sufficient to pierce the tank wall. The fuel ignition blew the fuel cap clear and spilled a bit of fuel in the process. As the fuel cap gracefully ascends, it leaves behind a mushroom cloud of sorts. This mushroom cloud is quite conductive, as evidenced by the high voltage pulses that play with it as it dissipates. Hostile machines have other susceptible critical components as well, such as the rubber tires and the electrical system. To test these possibilities, it's best to use a full-size test vehicle. Here we have a Ford Econoline 250 with a thick fiberglass top that's suitable for repelling medium to high voltage attacks. However, the fiberglass top might be the best attack vector. Now 24,000 volts is the maximum working voltage for this pulse-forming network. However, the temptation here is arguably overwhelming. 3, 2, 1. The high-energy strike pierced the fiberglass roof, strongly attracted by the electronics directly inside. Once inside, the high current strike liquefied the power distribution wiring, creating visible faults in the cabling and the electronic appliances. It appears that both the electronics and the cable plant were adversely affected by the boosted energy pulse. Currently, this 1 million volt machine has a strike range of about 30 feet. However, it may be possible to substantially increase the range of machines like this using an obscure effect called relativistic runaway breakdown. Current theories suggest that relativistic runaway breakdown could dramatically boost the strike range by a factor of 10 or more beyond classical discharges. This effect might have contributed to the mysterious super long discharges accidentally produced on high voltage towers at Russian test facilities over 50 years ago. This effect is also essential towards creating lightning strikes in storm clouds. So there's some interesting science here that may offer a way to adjust the frequency of lightning strikes over populated areas. No one has yet tried to build a machine big enough to recreate a relativistic runaway breakdown event in air. However, it should be possible for a sufficiently motivated person to do so. If you're interested in such odd pursuits, I plan to post pictures of my attempts to build such a machine right here in the near future.